Okay,
Okay, good. All right.
the
Good.
first
All right.
speaker in our famous experimental mathematics seminar at Rutgers University, the first speaker of this decade is Victor S. Miller from the Center for Communication Research. We'll talk about counting matrices that are squares. As usual, please mute yourself unless you have a question. Feel free to interrupt anytime and then ask a question and then mute yourself back. Thank you.
Okay. Well, thank you, Daron, for inviting me. And so let's see. Yeah, here we go. So where this all started was a request from Neil Sloane. I looked up my email on May 7th, 2013. There's a mailing list that a number of us are on called the Math Fun mailing list run by Richard Chappell. And Neil said, essentially, well, I'd like to count 0, 1 matrices, square matrices, which are squares of other such matrices. Now, he asked it in generality, but so immediately a few people started looking at the case when you're working in a finite field. In particular, you're working over GF2. Now, there's a lot of problems start out one way and they morph into other problems. So did this one. So basically, what I ended up answering, and I'll be a little more specific what I meant by an answer. Well, of course, in one case, the answer was I was able to calculate a lot of terms of this sequence, and then I'll talk about how that happened. So basically, what I was able to do was I can count squares in n by n matrices over the finite field of q elements, and also those which are invertible matrices when q is a power of 2. You can ask this question for other q's, which I'll discuss near the end, that gets a little more involved. So I haven't completely answered that. So basically, to set terminology, I'll set AN be the number of squares of matrices in n by n matrices over the finite field of 2 elements, and BN be the number of squares of GLN, or F2, in other words, the ones where the matrices have to be invertible. So here are some of the sequences that I've calculated. I went a lot further than that, but as you'll see, the numbers grow very quickly, so it would be sort of pointless to show these huge numbers there. And so here's how these sequences start. So the real question is how do you approach a problem like this? Well, first of all, I'll talk about why did I think this is a good problem? Well, I think a good problem is one where you get to learn not only solve the problem, but you get to learn about a lot of other things that maybe you don't know about before. And so one of the things I learned about, and this is a big subject, so I've hardly scratched the surface, is something called word maps and groups. So this is actually, at least for the invertible matrix problem, this is actually one particular case of the problem of word maps and groups. And then this filled another gap in my background, is something called the cycle index for matrix algebras. There is something which you might be a little better known, which is Polya's cycle index for the symmetric group. But it turns out that there's an analogous but slightly more complicated version of that for matrices over finite fields. And one thing which this was sort of a pet peeve of mine, which I'll discuss a little later, was Dixon's formula for the size of conjugacy classes. I'll talk about how this came about and how this sort of caused me a lot of head scratching for about a day until I found the answer. And then there's something which those of you who are pretty much into partitions may know about this. For example, there's a whole chapter about this in Andrew's book on partitions called Maynardis's Theorem for the Asymptotics of Classes of Partitions. Whenever you're counting something, you'd really like to have a good handle on how big the thing is and how it grows. And Maynardis's theorem gives you, at least in the simplest form, the main asymptotics of a lot of classes of various partitions. And then there was a trick which I sort of figured out on my own, but of course, like a lot of tricks, it probably was well known, but it deserves to be emphasized because it ended up speeding up the calculation by quite a bit, using logarithmic derivatives to get faster calculations for products of generating functions. So anyway, so a lot of what this is motivated by was a lovely article which was written back in May 1982 by the late Herb Wilf, and called "What is an Answer?" So it's probably a little too small to read. Here was a reproduction of the first page of this article in the monthly. But basically, the idea is we have some class of combinatorial objects, C sub n, for every integer n, and we'd like to get the exact number of such things. So what Wolf said was a good answer is an algorithm which calculates the exact number in time, essentially little o of the number of them. In other words, basically something more clever than just doing a clever enumeration of all the objects and tallying them up. And of course, as with all algorithms, the faster algorithm, the better. So little o may not be good enough, even though it's better. So, however, when you approach a problem like this, one of the things that you'd really like to do at the beginning, in absence of anything else, is try exhaustion. This, at least, if you're used to using the OEIS, this at least will give you a few terms of the sequence, and maybe you can use that to look up things and get some idea if it's related to some other problem, or maybe somebody's actually solved the problem in disguise, or maybe actually solved the problem. So basically, you might ask, well, you can generate all matrices, n by n matrices over GF2, and you could just enumerate them all, square them, and try to keep a tally. Of course, there'll be some duplicates because there might be more than one square root, so to speak, if there is a square. But you can do a little better an exhaustion because these things grow very quickly, so you'd really better make things fast. So the whole idea is you can interpret A as a bit string of length n squared, and you calculate a squared by some means, and you set a bit in a table, saying that it's actually a square. So the slightly cleverer way of doing it is to use a gray code. Now, some of you may know gray codes, but basically the idea of a gray code is that you enumerate all n-bit strings by flipping only one bit at a time. So it turns out if you keep b, which is the current value of a squared, when you flip one bit, which you get just by adding a matrix E to A, E with only one bit set, then in fact, when you expand out a squared, you get b is replaced by b plus ea plus ae plus e squared. But when you look at this, you find out that ea and ae just select one row or one column from a, and e squared is equal to e exactly when the one bit is on the diagonal, and otherwise it's 0. So it turns out that this leads to actually a nice C program, which I could give, but probably would be not too informative, just doing a lot of bit shifts and so on. And you can use this and you can calculate AN. And the calculation for n to 1 to 5 is virtually instantaneous on my Mac, but A6 takes about 1 hour, maybe a little less. But you can easily convince yourself, without thinking about it too hard, I started A7 and my computer crashed because it needs essentially 2 to the 49th bits, which even though bits have become cheap, it's not that cheap. So you can't go much further since the time is about 2 to the n squared. I mean, and the space is even is huge. That's the real problem. So here's the way of approaching a problem like this. You basically find what I'll call some nice set X, which contains the things you're interested in counting. And where the things you're counting are the elements of X which satisfy some easily described predicate. So, and then if you're lucky, you find some large group which acts, well, I'll have them act on the right, an X which is compatible with P. So in fact, that means when you apply any element of these symmetries to it leaves the predicate invariant. So then the whole strategy is you enumerate all orbits so that that predicate is true. And in particular, since we're working with matrices, it turns out the groups that we're going to work with act by conjugation. And the orbits are called conjugacy classes and usually written, x goes to x to the g. So for those people who are familiar with group things, so G sub A is just a stabilizer of a particular element A. And when you're working with conjugacy classes, it's usually called a centralizer. And X mod G are just the representative of all the orbits. And so the answer to your to your question is just the sum over all orbits which satisfy their predicate of absolute G over absolute GA. So of course this is an approach, so you have to figure out all the pieces in order to make this work. And sometimes, if you're really lucky, you can count all the orbits with the same value of the number of things in the stabilizer, which can get a shorter sum. So you can sometimes collapse them. So that's actually the case in this case. So since I mentioned word maps, even though I didn't really use it in any way except for what I'll say at the bottom, it's an interesting thing. So basically, if you have a group G, and W is a word in the free group in our generator, so it's just, you write x1 times x2 squared times x3 inverse or something like that. That actually gives you a map from R tuples in the group to the group itself, just by plugging in elements. And so it turns out there's a whole bunch of questions in this. There's a very active sort of subspecialty in group theory which studies these word maps. And so you might ask, what is the image of W? In particular, maybe how big is it? Or can you describe it in any better way? And it turns out, thanks to Zoom, I actually watched an interesting talk a few weeks ago where someone was interested in the measures that were induced by W. So you can ask, if the elements of the R tuples of G just are uniform, then it gives you a measure on the image, and you can ask what are its properties. So in particular, you can ask, how likely is something to be a square, for example. So a square is a very simple word. And so to give you an idea, what happens, there's this remarkable theorem of Michael Larson. So basically, he said, let G sub n be a sequence of simple groups where the orders go to infinity. And W is some non-trivial word. Then, in fact, if you look at the ratio of the logarithm of the size of the image of G sub n over the log of the whole group G sub n, then that limit exists and is equal to 1. So that says, it's a little weaker than what you might expect, but basically that says that the image of these things is going to grow really rapidly. It grows almost as fast as the size of the groups. So in particular, you might say, well, what's the group here? Well, if you look at only invertible matrices, they form a group. And as I'll mention later, they form a group which is based of finite index. So the probability of a matrix being invertible in the whole matrix, it turns out, goes to a non-zero limit as n goes to there. So basically, they're essentially, you're only off by a finite amount. So basically, it shows the image of WG is big. So that means that in our case, that AN has to grow approximately like 2 to the n squared. So even if you were really clever in being able to only enumerate over elements of which are squares, which then you'd still have a running time around like 2 to the n squared, which is just, you can't go very far if you do that. So
can I ask something about the
sure.
previous slide? Sorry.
Sure.
What do you mean by W of G? So W is a function from.
Oh yes. So this is sort of abusive notation. So W of G is the function which you get by plugging, plugging the elements into the word. So for example, if the word is x1, x2, then you have a map from pairs of elements of G, and the map, if you map the pair G1 comma G2 to G1 times G2, or if the word is x1 x2 squared, then you would map G1 G2 to G1 times G2 squared.
And what's W in the case when we're looking at squares?
Oh, W is just x1 squared.
Thank you.
Yes. Okay, it turns out that when I started getting into this thing about word maps, that power maps, in other words, where the free group that you're looking at only has one generator, are a real exception to the general rule. But on one hand, they're a little easier to analyze, but on the other hand, they have properties which are not shared by more complicated words. So for example, one of the more famous things in word maps is what's called Orr's conjecture from Oystein Orr, who conjectured that every matrix that the commutator subgroup of an invertible matrix actually could be written as one commutator. So the commutator subgroup, in other words, a commutator is just xy times x inverse y inverse for elements x and y, and the commutator subgroup is just a group generated by all such things. But Orr had this idea, which isn't obvious at first, that every commutator in a matrix group, you have to have some restriction on what the fields are, is actually just one commutator. And this was an outstanding conjecture which wasn't settled until maybe about 10 or 20 years ago. So it's actually very subtle. So in fact, since we're going to be working with conjugacy classes and matrices, we have to go back to describing conjugacy classes. Now, basically, most of us are familiar from our days with Jordan canonical form. But if you're working in Jordan canonical form, you really have to work over the complex numbers in order for it to work. And there's a slightly more subtle thing that happens when you are restricted to remaining inside a certain field. Basically, in order to describe the conjugacy classes in the group, you need partitions, which a lot of you are probably familiar with. But basically, the way I'll write a partition is it's a non-decreasing sequence of non-negative integers, where all but a finite number is 0. A lot of people just make partitions finite, but sometimes it's sort of useful to sort of have, a bunch of zeros at the end that sort of, it gets rid of certain annoyances. Not everybody feels that way, but in this case, it really helps. So basically, and if the sum of all these lambda i's, since all but a finite number is 0, the sum is some integer n, and we just write a lambda. I'm not sure how to pronounce that. In tech, it's just called a v dash. Lambda is a partition of n, and the elements lambda I, which are non-zero, are called the parts of lambda. So it's traditional to, and very useful to write partitions sometimes as what's called a Young diagram. So basically, you write a number of boxes, and the first row is just you have one box for every up to lambda 1, and the second row is all the boxes up to lambda 2, and they're all sort of left adjusted traditionally. So for example, the Young diagram for 5, 3, 1, 1, comma 0, and all zeros at the end is this structure there. And basically, there's one operation on partitions which is very useful, which is called conjugation. You can define it in the way I've given there. Lambda I prime is the number of j, so that lambda j is greater than or equal to I. But what it really corresponds to is you take the diagram and you flip it on the diagonal, and that forms another such diagram. The only requirement in the diagram is that the rows keep getting no longer as you go down. And you can easily convince yourself that that happens when you flip it by 45 degrees. And there's yet a third way of writing partitions, which is useful, which is the multiplicity, which basically asks you how many of these rows in the Young diagram, for given I, have a length I, have length I. And we'll see that we'll see it's useful later to go back and forth between multiplicity and conjugate and ordinary partitions. And just to get some idea, the asymptotics of partitions, the number of partitions of n is essentially, this is an old result. I don't remember who it's exactly due to, is 1/4 times square root of 3n times x of pi square root of 2n over 3. But the point is that it's actually...
It's Hardy and Ramanujan.
Yeah, Hardy and Ramanujan. And then later, Hardy and I think Littlewood gave a rather amazing, what today we would look at as an algorithm, but essentially an integral, which can make the exact computation of P of n in time. So
Rademacher was also.
Rademacher, yes. So basically, but the point of this is that the partitions grow, but they grow sub-exponentially, but they're still growing super polynomially. So that's something to keep in mind. Now, in fact, before I get into this, I'll get into a simpler but related problem, which will give you some idea of what's involved. So in Herb Wilf's lovely book, Generating Functionality, I think it's only in his second edition, not in his first, he asks and sort of answers the following question: how many permutations of n things are squares of other permutations? So the way that you approach this is, first of all, if you've looked at permutations, is that conjugacy classes of permutations are an easy one-to-one correspondence with partitions. So if you write a permutation in cycle form, the length of the various cycles correspond to the parts in the partition, and vice versa. And so you could say, okay, let an be the number of squares in Sn, and the first thing you notice is that squares are invariant under conjugation by other permutations. So in particular, you can use the strategy that I gave before. You can count conjugacy classes, and all you need is the stabilizer size for lambda. And it turned out it's not very difficult to see, and you can consult Wilf's book, that the stabilizer size for the conjugacy class corresponding to lambda is the product over all j of m sub j of lambda factorial. Remember, m sub j of lambda is the multiplicity, is the number of j's that actually occur in lambda, which could be 0, in which case that's a 1, times j to the mj lambda. Now, the nice thing about this formula is that it's sort of multiplicative. It decomposes. And that allows you to actually bring in generating functions. But before you do that, if you then look to see what happens when you square a permutation, you immediately see that all the cycles in the permutation, if a cycle is of odd length, it goes to, well, all the cycles act independently, so they don't mess each other up. And the cycles of odd length go to the same length, whereas the cycles of even length split up into 2 cycles of 1/2 the length. And a little staring at that will show you that something is a square if and only if the multiplicities of the even parts are even, with no restriction at all on the odd parts. So once you do that, you have the following. So basically, lambda is a partition of n if and only if, just practically by definition, the sum of j m sub j lambda is equal to n. And so you actually find the centralizer size is a product of independent factors. If you write down the generating function I should say the exponential generating function. So in fact, if you're familiar with generating functions, you'll see that some generating functions we'll write, sum of a sub n x to the n, and others you write sum of a sub n over n factorial x to the n. Now, it turns out that the n factorial in a lot of cases comes from the fact that there's actually an action of the permutation group. And by dividing out by the cardinality of the permutation group makes the remaining a sub n over n factorial have a nice form. And in this case, you find that that because you have this sum of j times mj, that the generating function, the exponential generating function.
Vector shouldn't be sine hyperbolic here.
Excuse me, shouldn't it be which?
For j odd, it makes more sense. This would be sine hyperbolic, or maybe I misunderstood.
Well, no, this is sine hyperbolic. Well, no, because j is even. This is
okay, so
yeah.
Okay.
Yeah, so basically the point of the top formula is that actually shows that the generating function, the exponential generating functions decompose as a product, for the individual m sub j's. And so for j even, you get the following generating function, x to the jm over j to the m factorial, but only when m is even, because that's the condition that we need. And that's just equal to the hyperbolic cosine of x to the j over j. Whereas with j odd, you have no condition at all. So you just get exponential of x to the j over j. And a little manipulation of the product of the exponential things actually shows that they end up being the square root of 1 plus x over 1 minus x. Because basically, you then, when you multiply all the exponentials, you essentially get the series for the logarithms. And then exponential of a logarithm, ends up, going away. But then you get this product over the hyperbolic cosine of x to the 2j over 2j. And so there have been a number of papers that have actually tried to look at what the asymptotics. I think the first one who actually gave the asymptotics is Ed Bender, who said the probability that a permutation is a square is asymptotic to 2 over square root of pi n times the product of k greater than or equal 1 of the cosh of 1 over 2k. Now that product actually converges to some particular number. But notice that there's a square root of n in the denominator. So that means that as n goes to infinity, that the probability that the permutation is a square actually goes to 0. And Wilf actually had a stronger conjecture that the a sub n was actually non-increasing, which later was also proved. And later, I think Flageolet and I forget who else actually gave a little finer asymptotics for this. They actually gave second order terms, but I haven't gotten there for this. But basically, the reason I bring this up is that the kind of analysis that was done with that is very similar to the analysis that has to be done with the matrix problem, but the matrix problem is a bit more complicated. So basically, in applying this to matrices, what we have is our set X, which is our containing set. It's a set of all matrices, and the predicate is true if and only if A is a square. So basically, our group that's going to act on this is the group of all invertible matrices, and it acts by conjugation, as I said, and it is compatible with Q. If something is a square, then when you conjugate by an invertible matrix, it's also a square, and conversely. So basically, we write, if A is conjugate to B, we write A tilde B. And in order to deal with the conjugacy classes, we need to talk about irreducible polynomials over Q. So I'll write script IQ as monic polynomials that are irreducible over FQ. And when I have a subscript of D, those will be those of degree D. Now, it's sort of well known, I think it even goes back to Gauss, that the number of irreducible polynomials, monic irreducible polynomials of degree D, is just 1 over D times that's the sum which I give. sum of E divides D. This comes from Mobius inversion. And so the other thing which I'll need is the other piece of notation, which if there's a more standard notation for this, I don't know, but this is the one I'll use. If phi is monic and r is a positive integer, then phi upper paren r is just the same polynomial whose roots are all the rth powers of multiplicity with the roots of phi. And that comes up in our analysis of the squares, as we'll see. And so in order to describe the conjugacy classes, we need companion matrices. So basically, phi is a monic polynomial. Denote by m of phi its companion matrix. Now, let's see. And if lambda is a partition, denote by m of lambda phi just the sum of the direct sum of the companion matrices of the powers of phi, raised to the parts of lambda. So if you think of this, go back to what you probably know in Jordan canonical form. If you're working over the complex numbers, the only irreducible polynomials are just linear polynomials. And so basically, what these companion matrices are just the Jordan blocks. And so basically, I'll call the elements which are conjugate to things of the form m of lambda phi a primitive conjugacy class. And it's one of the bases is that for different lambda phis, if lambda phi and nu psi are different, then and they're conjugate, then in fact the only way they could be conjugate is if the two pieces are equal. So and the person who first did this was Frobenius. And basically, he proved that every conjugacy class in matrices over a field is the conjugacy class, which is a direct sum of distinct primitive conjugacy classes. So in other words, you can get the conjugacy class by that. So every matrix is conjugate to a direct sum of distinct primitive conjugacy classes. Distinct where the polynomial has to be distinct. So you can't mix two different partitions with the same polynomial. So basically, what do we get when we apply it to the squaring problem? Well, it turns out that the same analysis which I have, even though I only calculated the things for over GF2, works for any finite field of size of power of 2. And so basically, Frobenius's result shows that all you have to do is find the squares of the primitive conjugacy classes. And so it turns out you can do a direct calculation, and you find that the square of m of lambda phi is conjugate to something I'll call m of psi lambda and phi upper 2. Remember, phi upper 2 is the polynomial which you get by squaring all the roots of phi. For some particular partition, which I'll describe, which is independent of phi. It just depends on the partition. So basically, let S just be the set of all partitions of the form psi of lambda, which I'll tell you how to calculate psi of lambda later. And if you let f sub phi of x be this sum over all the partitions in S of this thing, x to the degree of phi lambda, over the absolute value of the size of the centralizer of m of lambda phi. I'll call that the local generating function. And it turns out you can show that the generating function of a sub n over the size of gln is equal to the product of all of those f of phi. So that's, now of course this sweeps a lot under the rug, but this actually shows that when you're dealing with matrices, that the analog of the exponential generating function is one where instead of n factorial in the denominator, you have the size of gln. And so it turns out later that the size of the centralizer of m of lambda phi only depends on phi via the degree, that all irreducible polynomials of the same degree have the same size centralizer. So that actually makes things a lot a lot nicer. But basically, here's how you get psi of lambda. So if k is a part of lambda, it turns out when you start calculating, you find out that it breaks up into two parts. One is the floor of k over 2, and one is the ceiling of k over 2. So in particular, if k is even, it's just two copies of k over 2. But other than that, you know, if k is odd, you have a little difference there. So basically, when you work that out, you find out that psi is characterized by the multiplicity of I in psi of lambda is just this formula, which I give there for the multiplicity from the original from lambda. 2 of m2 lambda I plus m of 2, you know, so the two odd parts come from the fact that when k is odd, that you have a ceiling and a floor. And the factor of 2 comes from the fact that you have then two copies of k over 2. And the other thing is, when you're dealing with in a field of characteristic 2, it turns out that the mapping phi to phi upper 2 is actually a permutation on the set of all irreducible polynomials. So that really makes life very nice, because you don't have to worry about breaking up the polynomials in classes, because they're just all permuting around. So basically, I got that formula. And so the first thing that I did, being a fan of Neil's OEIS, is I exhausted over all partitions of n up to some point, and I calculated psi of lambda. And I got the sequence 1, 1, 2, 3, 4, 5, 7, 10, et cetera, and I looked it up in the OEIS, and that was A006950, which has a lot of information. And so I looked at all the things, and of course, some of the things had to do with partitions. So I said, this is really good. So in particular, it said the number of partitions of n in which each even part occurs with even multiplicity. Well, if you think about it, this sounds very familiar. This sounds exactly like what happened in the problem that Wilf gave about squaring of permutations. And there's no restriction on the odd parts. Same for squares for Sn. And it also said the number of partitions in which all odd parts occur with multiplicity 1. There's no restriction on the even parts. Well, I said, oh, well, that must be it. But then I looked at the values of psi of lambda, and they didn't have either property. So this caused me a little head scratching, because I was sure that this must have been it. However, I then decided to take their conjugates and see what happened. And in fact, they did have the latter property. So in fact, once I knew what I had to prove, then I was actually able to prove it, that basically a partition is psi of lambda if and only if the multiplicity of the odd parts of its conjugate are less than or equal to 1. And I did this by actually calculating an explicit inverse for that, which would work in that case. So basically, that if a prime of n is the number of lambda of n which have our nice property, then the algorithm to calculate all the individual products of the generating functions has to exhaust over all these. So we want to estimate how many there are. And so in particular, the A006950 gives the fact that the generating function for the a prime of n is so-called Ramanujan's, one of Ramanujan's Mach theta functions, which is written here. And by a little transformation, you can rewrite it as the product over all n not congruent to 2 mod 4 of 1 minus x to the n inverse. So in particular, now we actually have to count the conjugacy classes of squares. So basically, every irreducible polynomial has a set of allowed partitions, which would make it a primitive conjugacy class of squares. And the generating function is, for that number of classes, is just what I give there, is that the product over all the irreducibles over the sum of the allowable partitions of x to the absolute lambda d phi. But in our case, all of these S sub phis are the same, the script S, which I gave before. So our generating function for the number of conjugacy classes is just the product of Ramanujan's Mach theta function evaluated x to the d to the power of the number of irreducible polynomials of degree d. So it turns out that there's a useful trick when one deals with these things in terms of generating functions. So there's this amazing looking identity, which it turns out is not too hard to prove once you know it's there, of 1 minus qx is the infinite product of 1 minus x to the d to the absolute value of iq sub d. And basically, one of the ways you can prove it is that you could take the logarithmic derivative of both sides, and notice that in fact it has to have, both sides have to have constant term 1. And so if their logarithmic derivatives are equal, since they have the same constant term, then they must be the same. And the logarithmic derivatives, after just a very little amount of manipulation, just gives the fact that the sum of d divides n of d times absolute iqd is equal to n, is equal to q to the n. And that it just falls right out. But it turns out when you apply this transformation to the generating function, which I gave above, then you find that you can get a generating function for the number of conjugacy classes, which is the one that I give here. And in particular, if you look at that, you can see that the poles of this, that it has the smallest pole that this has as a meromorphic function occurs at x equals a half. And that then gives asymptotics that essentially a prime of n is asymptotic to some constant, which you can get by plugging in 1/2 after you get rid of the bad terms into this. So it's a constant times 2 to the n. So the number of conjugacy classes essentially goes up like 2 to the n. So in particular, this would already give a good answer to the question, just by enumerating all of these 2 to the n conjugacy classes. So it turns out that you get this local function, and for the actual original problem, and all of the SV are the same. And it turns out that so then I had this problem of what's the size of the centralizer of these conjugacy classes? And I figured this must be well known. And I looked around for a few days, and I even came up with an erroneous version, which I convinced myself was true. But fortunately, I was able to check it against the things I had calculated by exhaustion and saw that it wasn't working. So I scratched my head for a while. But basically, here's the size of the centralizer. So Frobenius, in the same paper that he actually found the conjugacy classes, looked at how the set of matrices that commute with a given one of these primitive guys is just some vector space. And so he computed the dimension of this vector space, which is just the degree of the irreducible polynomial times the sum of the squares of the conjugate parts of the partition. And so, in fact, it yields this many matrices. However, of course, not all these matrices are invertible, which is what we want. So you need some correction factor. And it turns out the correction factor, if you look at the probability that a matrix is invertible, that Leonard Eugene Dixon found that if you multiply this amount by the product of this probabilities for all the various multiplicities, then that is the correction factor. And in particular, as I mentioned before, this R infinity of 2, 0.288, etc., is the probability that an n by n matrix over GF2 is invertible. So here's the question. I couldn't figure this out. And then suddenly I looked at my bookshelf and I found Leonard Eugene Dixon's thing. And you can see how long I've had this book because the price was $275 when I bought it. But Dixon actually proved the previous result in 1900. But I found, much to my amazement, that in at least 5 or 6 subsequent papers that and this was published in the American Journal of Math, which was not exactly an obscure journal, but in fact, they seemed to be unaware of Dixon's proof, and they ended up re-deriving it themselves. So in particular, in fact, this is even derived in one of the exercises in Dick Stanley's book on enumerative combinatorics, but I don't think he has a reference to Dixon either, strangely enough. So in particular, so you can then use this to calculate the values, and it appears that the asymptotics are that a sub n and b sub n. Remember, a sub n is the original problem, and b sub n is when the matrices are invertible, that they all seem to be asymptotic to some constant times 2 to the n squared. So basically, this would show that the probability that a matrix is a square actually has a non-zero limit as n goes to infinity. So it turns out that Wall proved a result similar to this for counting other conjugacy classes, counting semi-simple classes. And it turns out an analysis of his method shows that it actually applies more generally, and in particular, it applies to this problem. So I have to credit Richard Stang for pointing this out to me. It wasn't originally when I wrote the manuscript of this paper, I only said this appears to be true, and I don't know how to prove it. And he then wrote to me and said, "Oh yeah, don't you know? This just look in Wall, and this is how you do it." So it's a bit different than SN, where, as I said, the probability goes to 0. So basically, if you bound the running time of this, we have to iterate all over all these partitions, which have the odd parts, multiplicity less than or equal to 1. And if you plug this into Maynardis's theorem, you get that the asymptotics are sub-exponential, but they're still super polynomial. So it turns out that, I was able to do this. I went, using the system Sage, I was able to calculate this for all n up to 70. I probably could have gotten further, but the thing, the numbers were getting large. They were, like close to 5,000 digits by the end, or 5,000, 5,000 bits. But here's the other trick, which I wanted to mention at the end. So basically, in the core of the algorithm, you need to calculate a bunch of products of power series, like this, f of d to the nd, and nd actually grows pretty big. And I originally just gave this to Sage because Sage just does this, but I found it was taking a long time. But if you take logarithmic derivatives, then it turns out that that the dependence on n sub d is not bad at all, and it's very quick to calculate the right-hand side of that logarithmic derivative. And since you know that they both have constant term 1, again, going from the logarithmic derivative to the original series does it uniquely. And in fact, if you write it out as a linear system, you find that it's a lower triangular linear system. And so when I made that change, it sped up the calculation for n equals 14 from 318 seconds to only 1 second. So that was definitely a useful trick to remember. And basically, so there's a question of what about other powers? So counting squares in characteristic 2 is easier because the map phi going to phi upper 2 is 1 to 1. But an odd characteristic, you need to break up the polynomials into different classes. So some of the phi 2's are squares of irreducibles if you're an odd characteristic, and the partition changes. But it turns out there's a paper by Stephen Cohen who gives the decomposition of phi of x to the r when phi is irreducible, and that turns out to be the stuff that you need in order to figure out how many phis are in various classes. But you get similar but more complicated formulas. And right now, so you exhaust over all restricted partitions, and so is there a faster algorithm? Is it, can I do better than just exhausting over those partitions? Is there an algorithm which is polynomial time in n, which this algorithm isn't? And so there's also finer asymptotics for an and bn. As I mentioned, that Flageolet and company used Darboux theorem to get the second order term in the asymptotics. And so there would be a similar question of finding the next poles of these generating functions. And so there are analogous results for powers that are relatively prime to the characteristic of the field, but they get a little more complicated. And then you can also point out when you look at this, that this in principle, and in fact actually gives an algorithm. If I give you a matrix, does it have a square root? And if it does, for actually calculating a square root or maybe all the square roots. And it turns out you can ask, there's another sequence which would be nice to calculate. Well, I'll say the sequence of the maximum number of square roots of any matrix, of any n by n matrix. I haven't been able to calculate this sequence yet. It looks a bit hard, but that is probably on my list of things to do. So basically, the acknowledgement first and foremost to Neil for asking the question and for OEIS. I mean, where would we all be without OEIS? And Bob Goralnik and Jason. Oh, you're welcome. And Bob Goralnik and Jason Fullman gave me very useful correspondence. If you're really interested, Jason has a whole series of papers on probability theory on various kinds of groups and questions like this. And Richard Stong kindly explained to me, made sense out of Wall's analytic method and showing me that it actually applied more generally than what he had in his paper. And I can't say, thank you again for Duran, and here's Duran and Herb, and we miss Herb greatly. But that's all I have to say. Yes.
Thanks for your fascinating
You're
talk.
welcome.
I have a quick, any questions? Before that, I have a quick question.
Is
So
your
the
paper
probability-
available?
Yes, I have. My paper is an archive. I think I sent it to you. I actually haven't gotten around to making some changes to it. I have a slight error in the formula for the number of conjugacy classes, and I haven't added the section using Wall's method to actually prove the asymptotics. But I will get around to making that change.
Victor, if I understand correctly, the probability of a random n by n matrix being a square
Yes.
is practically finite?
Yes, that's perfectly finite. I didn't give it in I have it in my paper. I have the calculation to some number of places.
And is a number explicit? You know how to
Yeah, well, I can calculate it to a large number of decimal places. There's, as a number theorist, I would always ask, is this number transcendental? Undoubtedly, it is.
But how big is it roughly?
It's about point. It's about 0.3 something. If you let me go to my paper, I can actually bring it up.
It's okay, but I'm curious.
Sure.
Can you test it by simulation? Is it easy to decide whether a random matrix is a square?
Well, that's what I get. It depends what you mean by easy. In principle, what you can do is you calculate the Frobenius normal form, and then you actually calculate to see. Once you've done that, that gives you the partitions, and then you just test to see if the partitions have that condition which I gave. So there actually are some, in Magma and Sage and so on, there actually are standard things to calculate the Frobenius normal form. So it's actually pretty easy to test if a given matrix is a square.
So be interesting.
It's a little more involved to actually find the square root.
Thank you. Are there other questions? Well, let's thank Victor again.
Okay.
Thank you for coming.
Okay, you're welcome.
Thank you.
I'm glad to
Bye-bye.
be here.
Thank
Bye-bye.
Thank you. Thank you very much.
Thank
Oh,
you.
you're welcome.
Thank you.
Okay. Well, you're welcome.
Thank you, Vic.
Okay, you're welcome.